There is a massive blind spot in the history of our planet, a hidden era where the magnetic shield that protects us behaved in ways we are only just beginning to comprehend. For decades, we believed the timeline of Earth's magnetic reversals was a solid, continuous record, a reliable barcode carved into the geologic strata. But a groundbreaking study released just weeks ago has shattered that assumption. It turns out that our map of the past is riddled with invisible holes, entire chapters of planetary history where the North and South poles may have flipped back and forth in rapid succession, leaving almost no trace behind. We are not just missing data points, we are missing entire events that could rewrite our understanding of how the core of our world functions. This revelation comes from a high-resolution analysis published in late February 2026 by an international team led by the National Institute of Polar Research in Japan. What they have found is not a new rock or a new fossil, but a statistical ghost in the machine. By applying a sophisticated new model to the global magnetic record, they have identified specific windows of time where the data simply does not add up. These are the vanishing intervals, periods where the magnetic field likely collapsed and reversed, yet the geological evidence for it has effectively disappeared. As we analyze this report today, in March 2026, we are forced to ask a fundamental question. If the magnetic field flipped and we missed it, what else have we missed about the stability of the shield that guards our atmosphere? To understand why this matters, we have to look at how we measure these things. Usually, we read the history of the magnetic field like a tape recorder. As molten rock cools or sediment settles on the ocean floor, tiny magnetic minerals align with the North Pole. When the rock hardens, that direction is locked in forever. If you walk along a timeline of these rocks, you see a pattern of black and white stripes. Black for normal polarity, where the compass points north, and white for reversed polarity, where the compass points south. This sequence is called the geomagnetic polarity time scale. Until now, we thought this scale was largely complete. We thought we had a high-fidelity recording of the last 155 million years. But the new data suggests that our recording is skipping. The researchers used a technique known as adaptive bandwidth kernel density estimation. In simple terms, imagine looking at a blurry photograph of a crowd. Previous methods were like counting heads in that blur. You could see the big groups, but individuals standing close together merged into one blob. This new mathematical approach acts like a sharpening filter. It adjusts its focus based on how much data is available, tightening up in areas where we have lots of rocks and widening out where the record is sparse. When the team applied this lens to the last 155 million years, the smooth curve of history developed sudden, jagged interruptions. Specifically, they were looking at the frequency of reversals. We know that the Earth's magnetic heartbeat is not steady. There was a long period, ending about 83 million years ago, called the Cretaceous Normal Superchron, where the field did not flip for nearly 40 million years. It was a time of magnetic silence, but after that silence broke, the field became hyperactive. The frequency of reversals began to climb. What the new analysis shows, however, is that this climb was not a smooth upward slope. The data reveals 4 distinct dips or drops in the frequency of reversals that technically should not be there. These dips represent times when the number of recorded flips plummets, contradicting the overall trend of an increasingly unstable field. The researchers argue that the Earth did not actually stop flipping during these dips. Instead, the reversals happened so quickly, geologically speaking, that the rock record failed to capture them. These are what we call short-duration flips. If a reversal happens and then flips back within a few thousand years, and we are looking at sediment layers that only form every 10,000 years, that event is invisible. It is a ghost interval. The study confirms that we are looking at a history book with pages torn out. This is a critical realization because we use these magnetic stripes to date everything else in geology. We use them to track the movement of continents and the evolution of species. If our magnetic ruler has missing inch marks, our measurements of the past might be slightly skewed. If you appreciate deep dives into the complex mechanics of our planet that go beyond the headlines, this is the perfect moment to check that you are subscribed to the channel. We are tracking this story as the geological community responds to these new findings, and you will want to be here as we uncover more about what these missing timelines mean for our current understanding of the Earth. Let us look closer at one of these dips to see how the mystery was cracked. The study highlights a strange anomaly around 32 million years ago. In previous versions of the timescale, this period looked relatively calm. But recently, geologists working in the Ethiopian highlands analyzed a stack of volcanic rocks known as the Lima flood basalts. Because these lava flows erupted in quick succession, they acted like a high-speed camera, capturing a much higher frame rate of history than the ocean floor sediments could. Buried in that lava, they found evidence of rapid chaotic reversals that no other record had shown. When the Japanese team fed this new Ethiopian data into their statistical model, one of the mysterious dips in the graph smoothed out. The gap was filled. This proves the concept. The dip was not a pause in planetary activity, it was a pause in our ability to see it. The researchers have now identified 3 other major dips that remain unexplained. These are the unknown zones. They occur in the window of time after the Cretaceous superchron, a period where the Earth's deep interior was shedding massive amounts of heat. The existence of these gaps implies that the magnetic field was far more volatile during these eras than we ever suspected. We are looking at a planetary shield that was flickering on and off, undergoing excursions and full reversals that lasted perhaps only a few thousand years before snapping back. The implications of this are fascinating because of what usually accompanies a reversal. When the poles flip, the magnetic field strength drops significantly. It can fall to 10% or less of its normal power. During these weak periods, more cosmic radiation strikes the atmosphere, potentially altering cloud formation and impacting biological DNA. If there are 4 or 5 ghost reversals hiding in the data, that means there were 4 or 5 distinct periods of high radiation and weakened shielding that we have never accounted for in our climate or biological models. We have been trying to solve the puzzle of ancient climate shifts without knowing that some of the pieces were missing. The precision of this new statistical model, the adaptive bandwidth kernel density estimation, gives us a roadmap. It tells scientists exactly where to look. We no longer have to guess where the missing time is. The graph points to specific million-year intervals where the rock record is suspicious. This is leading to a call for immediate action in the geological community. The search is now on for high-resolution archives, stacks of lava flows, or rapidly accumulating ice and sediment that correspond to these specific dates. We are essentially hunting for the lost frames of a movie. However, recognizing the gaps is only the first step. The existence of these invisible reversals presents a paradox. The overall trend from the Cretaceous period to today shows a steady rise in reversal frequency. The dynamo, the engine in the core, is running faster and more erratically. But why? What physical mechanism drives the core to remain stable for 40 million years and then suddenly start stuttering like a dying engine? The statistical dips identified in February 2026 are not just errors in data collection. They are fingerprints of a process happening 3,000 kilometers beneath our feet. To understand why the magnetic record is so fragmented, we have to look deeper than the crust. We have to look at the interface between the molten outer core and the solid mantle. This boundary is the most chaotic landscape on Earth, a place where continents of rock float on seas of liquid metal. The new data suggests that the heat flow across this boundary is not uniform. It pulses, it changes, and it is these deep, invisible rhythms that dictate when the poles flip and when they stay put. But there is a complication. The missing data in the dips obscures the true rhythm. Without seeing those rapid-fire reversals, we cannot fully model the turbulence of the outer core. We are left with a tantalizing scientific mystery. We know the record is incomplete. We know that short-duration flips are hiding in the static of deep time, and we know that correcting this timeline is essential for understanding the long-term evolution of the planet. But identifying the statistical gap is one thing, explaining the physical cause is another. Why did the Earth exit a 40 million year period of stability only to enter an era of chaotic, rapid-fire flipping? What changed in the deep Earth 100 million years ago to shatter the silence? To answer that, we have to leave the statistical charts behind and dive into the physics of the mantle itself, where a billion-year-old game of thermodynamics is driving the magnetic chaos we are observing today. This billion-year-old game of thermodynamics is not played on a flatboard, but across the most turbulent, hostile landscape on the planet. To comprehend why the magnetic record contains these invisible gaps, and why the recent statistical analysis from Japan is so pivotal, we must visualize the engine room where the magnetic field is actually generated. We are talking about the core-mantle boundary, a region 3,000 kilometers beneath us. For a long time, geology textbooks treated this boundary as a simple, smooth sphere, like the pit of a peach sitting inside the fruit. But the new data forces us to abandon that simplistic image. We now understand that the sealing of the core is likely as complex as the surface of the Earth, complete with inverted mountain ranges, massive valleys, and colossal structures of hot rock that influence the flow of liquid metal beneath them. This creates a profound complication for the magnetic field. The geodynamo, the process that generates our protective shield, relies on the motion of molten iron in the outer core. This iron swirls and convects, driven by the need to release heat. However, The outer core cannot just vent its heat into a vacuum. It has to transfer that thermal energy into the solid mantle above it. This is where the physics gets messy. The rate at which the core cools, and therefore the intensity and frequency of its magnetic flips, is dictated entirely by how efficiently the mantle can absorb that heat. If the mantle acts like a thick wool blanket, the core retains its heat, the convection slows down, and the magnetic field can become locked in place for millions of years. If the mantle cools the core unevenly, it induces turbulence, creating a chaotic field that flips frequently. This mechanism explains the most significant anomaly in the data set, the Cretaceous normal superchron. This was the long silence we mentioned, the era ending roughly 83 million years ago when the poles refused to flip. The prevailing theory, supported by the new heat flow modeling discussed in the February 2026 report, suggests that during this time, the heat transfer between the core and the mantle reached a state of rare equilibrium. The machinery of the geodynamo was humming along so smoothly that it effectively stopped stuttering. The North Pole stayed north, the South Pole stayed south. It was a golden age of magnetic stability. But stability in a dynamic system like Earth never lasts. The new statistical curves reveal what happened next, and this is where the mystery of the dips begins. About 83 million years ago, that equilibrium shattered. The mantle convection pattern shifted, likely due to massive slabs of cold ocean floor sinking deep into the Earth via subduction zones, eventually crashing into the core-mantle boundary like ice cubes dropped into a vat of hot soup. This disruption broke the superchron. The core began to shed heat rapidly and unevenly. Consequently, the geodynamo woke up and became hyperactive. According to the standard model, we should see a smooth, steady rise in the number of reversals from that moment until today. As the core cooled down from the superchron, the flipping should have become more and more frequent in a predictable line. But the Japanese team's adaptive bandwidth analysis shows that the line is not straight. It is broken. The frequency rises, then crashes into a dip, then rises, then crashes again. These dips are the statistical shadows of a process we have not fully mapped. They indicate that the post-superchron destabilization was not a smooth ramp-up, but a violent, stuttering engine start. The physics implies that during these dip periods, the outer core was trying to reverse, but the conditions were not quite right to sustain a full flip, or perhaps the flips were happening with such manic speed that they became blur events. Imagine a spinning top that begins to wobble. Usually it wobbles, corrects itself, or tips over completely. The data suggests that during these missing intervals, the Earth's magnetic top was wobbling so violently that it may have tipped over and stood back up dozens of times in a geological blink of an eye. Because the sediment on the ocean floor accumulates slowly, particle by particle, over centuries, it acts like a camera with a very slow shutter speed. If the magnetic pole flips and flips back while the shutter is open, the resulting image is just a gray blur. The record shows average polarity, effectively erasing the event from history. This is a critical moment to pause and consider what we are really asking of the geological record. We are trying to reconstruct the behavior of a fluid iron ocean 3,000 kilometers down, based on the orientation of microscopic dust grains that settled on the seafloor 50 million years ago. It is a miracle we have any record at all. If you are enjoying this investigation into the deep physics of our world, and you want to be part of the conversation as we unravel more of these planetary mysteries, this is the time to verify that you are subscribed. We have more deep dives coming on the physics of deep Earth geology that you will not want to miss. Returning to the mantle, there is another layer to this rhythm that complicates the picture: true polar wander. The February report highlights this as a driving factor for the long-term trends. While magnetic reversals involve the magnetic field moving, true polar wander involves the entire solid Earth tipping over relative to its axis of rotation, like a shifting cargo on a ship, causing the whole vessel to list. This process happens over tens of millions of years and is driven by the redistribution of mass in the mantle. As heavy sections of the mantle sink and lighter plumes rise, the Earth rebalances itself. This physical wandering changes the location of the magnetic poles relative to the continents. It means that when we look at the magnetic data from 80 million or 50 million years ago, we are looking at a moving target on a moving planet. The researchers had to account for this wandering to isolate the signal of the reversals. What they found is that the dips, these missing timelines, align suspiciously well with periods of major mantle reorganization. It appears that when the solid Earth is undergoing a major shift in mass, the magnetic dynamo in the core enters a state of high-frequency oscillation, producing these rapid, invisible reversals. This leads us to a fascinating realization about the interactions inside the Earth. We often think of the magnetic field as a separate shield floating above us, but it is physically tethered to the crushing pressures and temperatures of the deep interior. The 4 dips identified in the study represent intervals where the heat flow at the core-mantle boundary was likely changing drastically. We are seeing evidence of thermal avalanches, where heat builds up and then is suddenly released, causing the magnetic field to spasm. The most intriguing aspect of this heat flow analysis is the correlation with the Lima Limo event mentioned in the first part of our investigation. The newly confirmed reversals at roughly 31 million years ago found in Ethiopian flood basalts sit exactly inside one of these statistical dips. This is the smoking gun. It tells us that the other dips are not empty. They are not periods of quiet. They are periods of noise that we simply haven't heard yet. The Earth was shouting, but our microphones were turned off. We must also consider the role of the inner core. At the center of the molten outer core sits a solid ball of iron and nickel, growing by about a millimeter every year as the planet cools. As liquid iron freezes onto the surface of this inner core, it releases light elements like oxygen and sulfur. These light elements float upward, stirring the outer core like bubbles in a carbonated drink. This chemical buoyancy is the primary driver of the geodynamo today. However, tens of millions of years ago, the inner core was smaller, and the dynamics were different. The gaps in our data might correspond to specific phases of inner core growth, moments when the crystallization process hit a hiccup or a shift in geometry, triggering a burst of rapid reversals that the slow-moving sediment record failed to catch. So, we have a mechanism, We have the heat flow variations driven by mantle convection. We have the destabilizing influence of true polar wander. And we have the statistical proof that our timeline is missing key events. But knowing that the events happened is not enough. We need to find them. The statistical model has drawn an X on the map of time, pointing to specific eras where the rock record is incomplete. The dip at 31 million years has been partially filled by volcanic rock. But what about the others? What about the dips that occurred closer to the end of the Cretaceous? These missing intervals are not just academic curiosities. They represent times when the Earth's shield was potentially compromised for thousands of years at a stretch. If the field was flipping rapidly, it means the average field strength was low. The planet would have been bathed in higher levels of cosmic radiation. We know that the atmosphere reacts to this. We know that the biosphere reacts to this. But because we didn't know these reversals existed, we have never looked for their consequences. We have massive geological archives, thousands of miles of drill cores sitting in warehouses around the world that might hold the physical evidence of these lost years, if only we knew where to look. The statistical dips have given us the coordinates. The physics of the mantle has given us the cause. Now, the challenge shifts from the computer screen to the physical world. The hunt for the ghost intervals is no longer a theoretical exercise. It is a directive for the next generation of deep-sea exploration. We need to find rocks that formed fast enough to capture the chaos. We need to go to the places where the Earth recorded its own instability in high definition. The answer lies in the deep ocean, but getting it requires a mission that targets the specific anomalies the Japanese team has uncovered. The hunt for these ghost intervals has effectively redrawn the map for global ocean exploration. We are no longer simply drilling into the seafloor to see what is there. We are now drilling with a specific set of coordinates in time, targeting the 4 distinct dip periods identified by the Japanese National Institute of Polar Research. These statistical anomalies, sitting between the 83 million year mark and the present, represent the most elusive targets in modern geophysics. The challenge we face is that the evidence for these rapid-fire magnetic reversals is likely buried in some of the most difficult-to-reach archives on the planet. To recover them, we must look away from the slow-accumulating abyssal plains of the deep Pacific, where dust settles too quietly to capture the chaos, and turn our attention to the high sedimentation zones where the Earth writes its history in fast forward. This requires a fundamental shift in how we utilize our deep-sea drilling assets. Vessels like the scientific drilling ship Chikyu or the Resolution-class platforms operated by the International Ocean Discovery Program are now being looked at as the primary tools to verify this statistical model. The goal is to find drift deposits, massive piles of sediment created by deep ocean currents that accumulate mud and silt at 10 or 20 times the normal rate. In these unique geological drifts, 1,000 years of history might be stretched out over several meters of core sample rather than a few measly centimeters. If we can punch a drill string into one of these drifts, corresponding exactly to the dates of the 4 statistical dips, we might finally see the magnetic signal resolve itself. Instead of a blur, we would see the rapid flickering of the north and south poles, caught in the act of flipping back and forth every few thousand years. The urgency of this mission is driven by what these missing intervals represent for the biosphere. We have long operated under the assumption that the Earth's magnetic shield is a relatively stable constant, only failing during the rare and obvious reversals that we have already mapped. But if the February 2026 analysis is correct, and there are clusters of short-duration reversals hiding in these dips, then the history of life on Earth is far more exposed to cosmic radiation than we ever realized. A magnetic reversal is not instantaneous. It involves a collapse of the field intensity, often dropping to 10% of its full strength, and this weak state can persist for thousands of years while the poles navigate their way to the opposite hemisphere. If the statistical dips hide not just one, but a series of rapid reversals occurring back-to-back, we are looking at intervals where the planet's shield was down for extended periods. This changes the variables for ancient climate models. When the magnetic field weakens, high-energy particles from the sun and deep space are free to smash into the upper atmosphere. This ionization process creates a shower of secondary particles that can penetrate deeper toward the surface. There is a growing body of hypotheses suggesting that this increased ionization can influence cloud nucleation, potentially altering global albedo and triggering cooling events or storm intensification. By missing these reversals in the record, we may have missed the trigger mechanisms for specific ancient climate anomalies that have puzzled meteorologists for decades. We must now cross-reference the dates of these 4 statistical dips with the known timeline of biological evolution. Paleontologists have frequently noted turnover pulses, periods where species rapidly go extinct or new forms suddenly appear, which do not always align with asteroid impacts or massive volcanic eruptions. It is entirely plausible that these invisible magnetic crises placed a unique stress on the biosphere. A weakened field leads to increased ultraviolet radiation, reaching the surface as the solar wind strips away the upper ozone layer. This would not necessarily cause a mass extinction, but it would increase the mutation rate and place heavy pressure on organisms living in high latitudes or shallow waters. We are looking at the possibility that the ghost intervals were actually engines of evolution, driving genetic change through radiation pressure during periods we previously thought were magnetically quiet. The search is also turning toward the rock record on land, specifically targeting volcanic sequences similar to the Ethiopian flood basalts that helped solve the 31-million-year mystery. Geologists are now scrambling to identify other laminated lava flows, stacks of eruption layers that cooled rapidly enough to act as high-fidelity tape recorders. The focus is shifting to large igneous provinces in India, the North Atlantic, and the erratic volcanic chains of the Pacific Ring of Fire. If we can find lava flows that date to the specific windows of the remaining 3 dips, we can bypass the ocean sediment problem entirely. Lava freezes the magnetic field direction instantly. It is the gold standard for this kind of detective work. However, the implications of this study extend beyond the past and directly into our future. The new statistical model confirms that the geodynamo is capable of behaving erratically after long periods of stability. We are currently living in a period where the magnetic field has been weakening for the last 3,000 years, and the South Atlantic anomaly, a region of particularly weak magnetism, is growing. For years, scientists have debated whether this is a sign of an impending reversal or just a normal fluctuation. The discovery of these hidden dip periods tells us that the Earth is capable of entering phases of rapid, stuttering oscillation that previous low-resolution records simply smoothed over. We might not be heading for a clean single flip, but rather a chaotic interval of instability, similar to the ones hidden in the data from 50 or 60 million years ago. This realization forces us to reevaluate our confidence in the long-term stability of the field. If the rock record can hide a reversal that lasted 5,000 years, then our understanding of reversal frequency is fundamentally biased toward long, stable events. The danger is not that the poles will flip tomorrow, but that our models of the core are tuned to a simplified version of history. We are trying to predict the behavior of a chaotic system while missing 10 or 20% of the data points. The work done by the team at the National Institute of Polar Research is akin to cleaning a dirty lens. Suddenly, the image is sharper, but the picture it reveals is more volatile than we expected. As we look forward, the integration of this new adaptive bandwidth statistical method with artificial intelligence and machine learning offers a promising path. Researchers are beginning to train AI models on the existing patchy magnetic data to predict where other, smaller excursions might be hiding. We are moving toward a predictive geology where the math tells us where to dig. The 4 dips identified in the February report are just the largest, most obvious gaps. It is highly likely that as the resolution of our models improves, we will find that the magnetic timeline is fractured by dozens of even smaller, faster events, micro-reversals that lasted only a few centuries. The next decade of geophysical science will be defined by this hunt. We are no longer satisfied with the black and white barcode of the geomagnetic polarity timescale. We need the grayscale. We need to see the wobble, the hesitation, and the collapse of the